Okay. Okay, so we have a little less than an hour, and I wasn't going to do anything new theoretically today, but I do have some material on spacecraft that are not rigid, flexible spacecraft that I think it will be interesting to cover starting tomorrow, if that sounds like a good idea. I have a couple comments on the gravity gradient problem. I didn't have time to, sorry, to look at the model that I have. But I have some thoughts about the initial conditions, and maybe you've already solved it, so that's perfectly fine.
Yeah,
Yeah.
yes.
Yes,
Yes.
we have fixed some problem.
We have initialized the angular velocity with the value of the orbital angular velocity.
Aha, that was the
Yes.
other. Yes, exactly.
But we have also some problem with the transpose of the matrix, so
Yeah,
the initial value of the angular velocity was not the only error.
yeah, it shouldn't be 0, right? Because I think it was 0.
It was 0, yes.
Yeah. So that and the initial position. So I'll show you the for those, maybe it's interesting for those who haven't done it yet. And again, it's not a requirement, that I think it's a nice to have since we started it. So basically, what I gave you is the following situation where you have the ECI axis, X, Y, and Z. You have a spacecraft that is at the initial time somewhere on the x-axis, so this is its initial position, r0, and its velocity is pointing somewhere in the positive y, not somewhere, actually in the positive y only. And so the corresponding LVLH, the way we defined it, will have, I'm going to draw it somewhere else. We'll have A3 pointing towards the center of the planet, of course, anti-parallel to X. A2 will be anti-parallel to Z, right? And then this will be A1. So I was struggling to visualize if this made any sense for one quaternion, but I don't think you can represent, basically you can't go from X, Y, Z to this orientation, because that's how you need to define your initial orientation of your spacecraft with just a simple one quaternion that you can visualize, but you can break it down. And so I was thinking one way to compute the initial condition for quaternions is, you start from the axis for ECI like this, axis 1, 2, and 3, and you perform a rotation of 90 degrees about this one, and this will be the rotation axis. So the angle for this quaternion is 90, and the Eugen axis is obviously a 0 minus 1, because I'm doing it going in 0. And correct me if I'm wrong. So there is this rotation, and then there is a second one, because this will bring, let's see, will basically bring me in this configuration where 1 now is pointing up, 3 is pointing in, if you like, and 2 is still there. And so to end up into this configuration, which is my desired initial condition, it will be another 90-degree rotation, this time about the axis, which is the yaw axis, right? But the E in this case is minus 1, 0, 0. And remember, I'm expressing E with respect to ECI when I do this. And so my two quaternions, if this is correct, since the angles are both 90 degrees and I divide by 2, basically you see sines and cosines of 45 degrees. Sorry, there's no space here. My, I guess, first quaternion would be 0 minus square root of 2 over 2, 0, 0, right? Because it will be, this is the term with the cosine of pi over 2, which is 0. And these are sines of pi over 2, which is square root of 2 over 2. So there is a minus there. And then Q2 is, well, I have minus square root of 2 over 2 at the first component, and then 0, 0, 0. So I can break down this initial condition just because it's a very nice initial condition with the axes that are kind of parallel to each other. So in general, maybe not that easy to do. But in this case, I think you can break it down that way. And so then there is a if I share my screen, this slide here in one of the lectures shows you how you can multiply two successive rotations using quaternions. So in other words, in my case, I would have to put the Q prime quaternion would actually be, let's see, which one of the two? Oh, first you do the first rotation. It will be the second one, right? Agree? No one is talking.
Yeah.
I think so, right? So if you put it
Yes.
in a matrix form, I think one of you was getting a 0.5, what it was, 0.5?
Yeah, 0.5, 0.5, minus 0.5, and minus 5.
Okay. So if these are my two quaternions and this becomes my, so the quaternion that I have to put to the right of the product is the, I guess, the first rotation. So this will be my Q second, I think. And this should be my Q prime. Okay. So if I do it that way, no?
Yes, I mean, the quaternions are not normalized this way.
Good point.
I think the last component should be still radical 2 over 2.
Oh, yeah. Sorry about that. Yes. Yeah, I was going to. Why am I doing square root of 2 over 2? I'm making a mistake here. This is pi over 2. Oh, 45. Yeah. Okay. I was dividing 90 times 2 for the sine, but not for the cosine. Good. Thank you. Yes. Okay, so now it makes more sense. Still, this should be the order, and I believe if you apply that product, I mean, we can do it if you like, but I think you get exactly what Alessia was saying. Do we want to do it, or you can do it by yourselves? So in other words, takes these elements and populate the matrix that you see there with the elements of this quaternion. And then this is going to be the vector that you multiply by that matrix, and I think you would get probably what you see, the 0.5 minus 0.5, etc., etc. Is that how you're doing the initial condition, or for those of you who have done this?
Yeah, no, actually, I've derived the direction cosine matrix, and then I extracted the quaternion from the direction cosine matrix.
Okay. Well, just for curiosity, since we're here, I'm going to do it. Q, so this will be my Q second, basically. And I think it's 0 minus square root of 2 over 2, 0 square root of 2 over 2. I guess I didn't have enough coffee today. I'm forgetting elements here. And this is my Q prime is equal to minus square root of 2 over 2, 0, 0, square root of 2 over 2, right? Okay. So in my matrix, I see, let's see. Okay. This would be a square root of 2 over 2. Q3 is 0. Q2 with a minus, so I have square root of 2 over 2. Q1 is 0. I mean, I'm talking about this first quaternion, the Q, the one with the second superscript. Now this is definitely multiply minus square root of 2 over 2, 0, 0, square root of 2 over 2. Minus Q3, still looking at this one, is 0. Q4 is square root of 2 over 2. Q1 is 0. Q2 minus square root of 2 over 2. Then I have a Q2 here, which is another minus square root of 2 over 2. 0. Square root of 2 over 2. Q3. 0. Almost done. Another 0 here. A square root of 2 over 2. Check my signs, please, because I'm sure I'm making some mistake somewhere. So let's see what this looks like. Can you see my piece of paper okay, or it's super tiny?
If you can stop sharing the screen, I think it's better.
So yeah, so if we said that this is the quaternion that we call q second in that equation, and it was 0 minus square root of 2 over 2, 0 square root of 2 over 2, and then the other one is minus square root over 2, 0, 0 square root of 2 over 2, I populate this matrix here using this quaternion, and that I think is what I get. You can check again. That's right. That's a 0. That's yeah, with a minus in front. That's a 0. Then I have 0 here. Fourth component, right? That's a 0. Second component. Then I have second component, first, last, third. Then I have first, which is a 0. The second with the minus. Third, which is 0, and fourth. Okay. If I start multiplying, the two quaternions, or I guess the matrix and the quaternion, I get a minus 0.5 first element, right? Yes. This is, yeah, minus 0.5. Another minus 0.5. A 0.5. And a 0.5. Is that what you have?
No, the sign are the opposite, I think.
Okay.
The first two components positive.
Yes, the first two components positive and the last two negative.
Interesting. Unless I'm using that product matrix times quaternion the wrong way. But I don't believe so, because I go from C to B and then a B to A. So usually, well, if what I have in this slide is not some big memory that I put in there by mistake, if you change sign to all the elements, it's the same thing. Is that what you have? You have 0, 5, 0, 5, 0, 5, and minus, minus?
Yes.
Okay. So it may be actually the same thing. Questions on these? So I did this just to show that what we tried to do last time, going through the DCM, doing computationally, getting the DCM and then extracting the quaternion, that's perfectly fine. But there are ways to actually visualize and compose rotations by hands ahead of time, sometimes, like in a case like this. Okay. So if there are no more questions, I really would like to check the pulse of the class. I have almost everybody's homework 1. If you can send it to me if you haven't done so yet, please do. How are you doing with the second one? Is anyone willing to share something that is well developed, so that we use this hour as, as if I were walking around the class and looking at your work? And I guess my question for everybody is, if you feel like you're in good shape with the second homework, do we need more time together working on it, or I can just go on with more theory and other things that I knew? Hopefully. What's the thought?
Professor, I have a question on the second homework on what we did together last time.
Yes.
So maybe I can share my screen, and also because I went
Yes.
also from, okay. Sorry. Let me check. Okay. Okay, so when we defined last time this function here, okay, oh no, sorry, this was the one where we stopped. Okay, this one was the one that we defined together. Okay, so basically what we did was to define the matrices C1, C2, C3. And then following what we did last time, we also defined these three matrices, AG, AS, and AT. And my doubt is, I mean, the elements of these three matrices that we defined are essentially just a rearrangement of the elements of the matrices C1, C2, C3, right? Because
Yes,
we gave initial conditions for AG, AS, and AT already in the reference frame of the body,
yes.
right?
Yes.
Okay, so when using those as initial conditions, so for example, this one, I don't know, I mean, it was not even necessary to perform the scalar products. Here I wrote the same essentially code that we wrote last time, but it was not necessary, right?
No,
Because
I think, yeah, since they're already expressed in that basis, the way I believe we put together I'm looking at my notes, I believe the C matrices are with the AG as the first column, then the AS as the second column, and the AT as the third.
okay, so as a notation,
so that's what you should
AG. Sorry, I mean, as a notation, what we call the here hey G is the same as G, what we call G.
Yeah.
Okay, okay.
Yeah.
Okay, but
verify that this is working just for fun. Run. It's a little noise. Run this code and compare the C columns with just you know the pictures, but it should definitely. I mean, AG is constant in the body axis, right, or not? Which one was constant? Yeah, AG is constant. And so that should be only. Can you go up?
I should run this?
No, up in your code. The editor, yeah.
Because the problem is that it won't run because I have now.
No, don't run it. If you can just go up in the script, I want to see the definition of G. Yes, the scroll up. Yes.
Okay, sorry.
Okay. I see G. But G0 is probably what was it? The 0? No, it was a function. I don't remember.
Yes, G0 was
1 0 0. So yeah, you thought that with 1 0 0 you get 1 0 0 for each component. So and then you've done it in the right way. It's just I don't see a problem the way you've done it, but it should give you the matrices that are the same as if you were putting the G, S, and T or AG, AS, and T as columns. They should come out the same thing.
okay. Yes, but still I think it is convenient to keep also these functions as an output because they are useful then to define the following matrices.
Absolutely.
Okay, so what I did next, I kept writing the function that we stopped writing last time, so the one integrating omega of the body. So sorry, I didn't know how to split it in more lines, so it's very difficult to read. But obviously for this function, I also kept JTotal as an outcome because it's convenient then to use later. So where JTotal also contains the terms relative to the three momentum exchange devices. And obviously here we do not need also AT, AG, and AS as arguments for the function, right?
No, because you're basically calling them by saying, for example, C1 parentheses column comma 1. That's how you are. That's how you're calling them, basically.
Yes.
Can I show you? Can you show you something real quick? Can I take control of your screen real quick?
Sure.
Just because I think it's easier to see things. You can do this. Wow. That's not doing it.
You need the keyboard.
So if you don't want to go overboard with your functions and, you know, you can keep things in the same kind of window and see everything by doing things like that. The 3 dots, and then you go next line.
Okay, thank you.
Yeah, just because otherwise it becomes a nightmare to go back and forth, right and left.
Yes, in fact it was. Okay.
Maybe I should. I don't know if it needs to go after a plus, or it doesn't matter where you put it. Yeah, I think it's fine like this. Yeah.
Okay. So what I did next was to use the equation that we derived for omega dot.
Yes.
So we needed we defined J total, so that then we have the inverse of J total that multiplies all the other terms. And I think that this should be correct. I hope I didn't make any mistakes. So just one thing that I wanted to ask about this formula. Okay, here we have it. Since we have the same inertia matrix for all the 3 devices, right?
Yes.
Okay, so we can always put them in evidence, right? So
what would you like to put outside?
Yeah, in the summations, I mean.
I mean, I'm not sure I'm following.
Yeah, for example, in the term that contains the summation of gamma j double dot time y gj times gj.
Oh, I see.
That would be my first term. Let me see. So what I wrote was y with 1, because it's the first component to be yg, right?
Yes.
Okay, that multiplies the summation of the 3 terms with gamma double dot. Then Gj should be Cj with 1, as we defined it.
Yeah. Yeah,
Okay.
it's the same. So you're going to use them.
Okay, so so I have then what I did was to integrate this numerically. And then I also kept the total inertia matrix as an outcome. And then I was starting to, I don't know if it is convenient, but I was starting to write the function that gives me the capital B, capital C, and capital D matrices for the control vector. Okay, and here it was convenient to use AG, AS, and AT because their columns are what we need to define BC and D. So, okay, B, since we have Y that is the same for any device. Then the B is multiplying, we have AG from our definition of AG times Y times the identity matrix, right?
Yes, you have all the gimbal axis moments of inertia in a diagonal, then multiply all the G vectors in columns, one after the other. Is that what you get?
Yes, because AG that we obtained for the previous function, let me check it. Okay, has as columns AG1, AG2, and AG3. So it's exactly the matrix that we need.
Oh, okay. Okay.
Okay, then D was as simple. Sorry?
So what is Y again?
Y, oh, sorry. Y1.
Right, so
Oh, sorry.
also, let's see here. Your G is in a column form. So the columns of AG are the G vectors, right?
The columns are the G vectors. Yes, I think they are. Yes. Or not? Not yet.
It looks like they are. It should be. So
sorry, do I need to transpose this? But I don't think
that's
so.
that's what I'm thinking. The way you wrote it, the Y is the same. The YG is the same for all of them, right? As a value. So yeah, I think you need to transpose because this is what I mean.
A second.
Let's see. I'm switching my camera. Maybe if you stop sharing for a second, this is bigger.
Sure.
So in the notes, I think you're still sharing. Okay. In the notes, if you recall, B is given as a matrix that has the G vectors as columns, and then this matrix diagonal that has only the gimbal axis matrix moment of inertia on the diagonals. And so in our case, it's only 3 of them, so G1, 2, and 3, and these are all identical values. So just to be quick and see what the outcome should be, if I take these and well, that gives me P transpose, though, forget it. Oh my goodness. Okay, so yeah, I transpose both, transpose everything. So this is what I get, this is what okay, no, I think you have it right then. G1, so you should have G1, the final result is G1, G2, G3, still has columns, they multiply basically just this guy, the YG, which is identical for everybody. So I think you're right. Okay. Just checking.
Okay, no, yes, because I had the same doubt.
Yeah. So I transpose both sides. I take these matrix, transpose it's the same, and then this becomes a column, and this is what I get. But then this is the transpose. So yeah, that's what you have as B. Okay.
Okay. Shall I share again?
Yeah. Go ahead.
Okay. Okay, so then, okay, I was left, I didn't have enough time to complete this. Okay, what we need now is to write C, that is the most, obviously D is the same for D, because always for the spin inertial moment we have that it is the same, so it's the identity matrix, and we just multiply it times AS.
Okay.
So now instead we need to write C. Okay, so there are two difficulties in writing C because I need to define a matrix that has on its diagonal the capital omegas. And I don't know if there is a way to avoid it, but I think it's not because they are different.
Yeah, they can be different.
Okay, so we need to first define this matrix, possibly.
There is a command that is called diag in MATLAB, and I think if you put diag and then inside the vector, it will provide the diagonal matrix.
Okay.
Maybe it just understands diag of omega g. That's already or q. Whatever. If that's already a vector, I don't know.
Still like this. Okay.
A second.
Okay. Then what else do we need? So the first term of C will be again ESW times AT times this matrix M that I defined, right? Is the first term. So again, using that ESW is the same, so the matrix with all the diagonal elements equal to ESW 1, 2, and 3 is ESW times the identity matrix.
Yes.
Okay. And then we need to define also the skew-symmetric matrix that corresponds to small omega. And I don't know if there is a way to do that easily. Sorry, I need just to find the expression for this.
Well, it's just in reality it's a cross product. So one way to do it is you do.
The problem is that it's
a matrix. So
yes, because it's a matrix. So we need to define it, I think.
It's actually multiple cross products. That's why.
Yes. Sorry.
You're fine. This is more or less what I would do if we were in an actual classroom.
Okay, here we have it. So it should be 0 minus omega. Okay, this is omega of the body, so it's on B, right?
Yeah.
3.
Okay. Is it 3, 2, 1, right?
Yeah. Then it's correct. And then no?
I think so. I'm just looking. Yep.
Okay. So here the second term should be x star ag. And we have Okay, this is the second term. Okay, now we have this last term where we need, okay, to write this matrix here.
Mm-hmm.
Okay, this is the most difficult one. Okay, first for sure, we have S is the third, right? Or the second? No, it's the second.
Second.
Y2 minus Y3. Again, the last difference between the two matrices can be just written as this times the identity. I have also one factor. And also omega plus omega d can be put outside, right?
Yes.
Oh no, oh, maybe not, because
No, it's matrices.
yes, it's a product. It's the vector.
I mean, I'm thinking. Well, you can write the matrix that contains all those T S transpose plus S T transpose, and then once you have the matrix, you multiply times omega B plus omega D, something like that. I think.
So we need to write. We can define. I don't know. Maybe. Is it the one? I'm terrible at finding the name for things. Okay, so T1, I'm starting to define the matrix T1 S1 transposed plus S1 T1 transposed. Okay, so T1 is, let me check again how we defined.
It's your 80. It's your 80. Yeah, sorry, I just at some point. I think, wasn't it?
Sorry, I didn't.
I thought at some point I just gave up on the AGA, etc., and I just called them ST, etc. But that's what they are.
Yes, in fact. So it's AT should be.
Yes. Yeah. So GA, S, and T will be the columns of the matrix CJ, but since they are effectively AG, AS, AT, and we basically made the switch right at the beginning to just call them GS and T. Or at least I did.
Yeah.
Yes, transpose, S, transpose, yes.
Okay, so maybe since we need the vectors that we obtain from the row by column product of these three matrices times omega plus omega des, maybe we can simply define already these three vectors.
So those are matrices. It should be 3 by 3 matrix. Oh, okay, yeah, yeah, you can do that, yeah.
I think that then we can define directly. Okay. Sorry if I'm very slow, but I've never used it. Okay. And then here we have the matrix that has these as columns, right? So it should be simply E1, E2, E3.
I hope we're not making too quick assumptions and simplify matrices into scalars, but this should work because they are identity matrices anyways. So yeah.
Yeah, I think we can do that because anytime we have, for example, YG, we can put it out of the matrix and then we have the identity matrix, and if we perform, for example, the first multiplication, then it returns the same matrix that we have on the left.
Mm-hmm.
Okay. Okay, so now we have B, C, and D.
Yes.
And I don't know, is it convenient to put them together in the matrix Q so that we can use just the vector eta, or
Yes.
I don't know. Yes?
Yeah, you can put Q is D and C, basically.
So I don't know if we want to write another function.
Up to you, really.
Okay.
You can actually, you could put everything here and even output directly the final control vector if you want. It's up to you how modular you want to make this.
Yeah, maybe. I prefer to use separate blocks because it's easier than. Okay, so and also I don't know if we want to neglect the term containing B or not.
Well, do you have it in your dynamics? I think you do. So you're not
Yes.
neglecting.
No, I mean if we want to neglect gamma double dot.
Oh, for well, it's up to you. You can. I think you can turn it on and off easily. You comment it out when you want to include it or don't. It's part of that T torque momentum exchange device that eventually will go into the final form for eta, which is that product of different matrices, etc. And then there is this TMED, torque momentum exchange device, which is everything, and you may include the big gamma double dot as well in it.
Okay, so we want to put it in the torque essentially.
Yeah, you can. Yeah.
If now I want to, okay, so I don't put it in Q. That was my.
Oh no.
Okay, so Q should simply be
DC. So I'm sorry that, as I told you, I have to go. I'll stay 15 minutes longer tomorrow. So, would you want to continue with this tomorrow together for a little bit longer? Because I think, again, one of the purposes of the class was working on Simulink together. So I'm fine if we continue with this. And then, since we have some extra time, I'll continue with more theory that I'm not going to ask you to run anything from, but like with gravity gradient, I think it's additional work that may be useful and interesting. Does that sound like a plan, or you're done with homework 2, you don't want to see this anymore? I think we can spend some more time working on it, right?
Yes.
All right, sorry again for leaving earlier than planned. Conflict that came up. Tomorrow I'm looking at the schedule. So tomorrow we can do the first 2 hours and stay a little bit longer, and we'll make up for the time. Okay?
Okay.
Thank you.
Thank you.
Okay.
Thank you. Bye.
Okay, thank you.
Ciao,
Bye bye.
buonasera.
Bye.